Friends, welcome to the tutorial series on network analysis made simple. This is a module-wise ECE Network Analysis paper solution series. In this tutorial, we are going to solve VTU CBCS scheme network analysis paper questions of December 2016, January 2017 paper of module 4 of syllabus 15 EC34. Friends, I prefer to emphasize on basic concepts, strategy and thinking process rather than detailed mathematical steps. I am sure you are well equipped with relevant mathematical skills required. Hope this tutorial will ignite some of your thoughts. Let's go ahead. Friends, first let us answer the question on resonance circuits to prove that F0 is equal to square root of F1 into F2, where F0 is the resonant frequency and F1 and F2 are the lower and upper half hour frequencies. Consider the series resonance circuit drawn and the frequency response curve. At both half hour frequencies, current I is equal to I0 divided by root 2, where I0 is the current at resonance. We also know that I0 is equal to V divided by R at resonance. By substituting for I0, we get I is equal to V divided by root 2R. But current at any frequency will be I is equal to V divided by Z, and that is equal to V divided by R plus J into bracket XL minus XC. Here we are assuming that XL is greater than XC. So we get I is equal to V divided by square root of R square plus XL minus XC whole square. By equating the right hand sides of both equations, we get V divided by root 2R is equal to V divided by square root of R square plus XL minus XC whole square, from which we get root 2R is equal to square root of R square plus XL minus XC whole square. Equation 4 will be true when XL minus XC is equal to R. But by observing the frequency response curve, we find that at F2 or omega 2, XL is greater than XC. So, at omega 2, XL is equal to omega 2L and XC is equal to 1 divided by omega 2C. By substituting the values in equation 5, we get omega 2L minus 1 divided by omega 2C is equal to R. By solving it, we get a quadratic equation in omega 2 as omega 2 square LC minus omega 2 CR minus 1 is equal to 0. By solving for the roots, we get omega 2 is equal to RC plus square root of RC square minus 4 into LC into minus 1 divided by 2 times LC. Note, only positive sign is taken before the square root to ensure that omega 2 is always positive. Similarly, at F1, we find that XC is greater than XL. Hence, equation 4 obtained earlier can be written as XC minus XL is equal to R. But at F1 or omega 1, XL is equal to omega 1L and XC is equal to 1 upon omega 1C. By substituting, we get 1 upon omega 1C minus omega 1L is equal to R. By solving and rearranging, we get the quadratic equation in omega 1, this time as omega 1 square LC plus omega 1 into RC minus 1 is equal to 0. By solving for the roots, we get omega 1 is equal to minus RC plus square root of RC square minus 4 into LC into minus 1 divided by 2 times LC, from which we get omega 1 is equal to minus R by 2L plus square root of R by 2L whole square plus 1 by LC. By multiplying equation 9 and 7, we get omega 1 into omega 2 is equal to, in one bracket, minus R by 2L plus square root of R by 2L whole square plus 1 divided by LC into, in another bracket, R by 2L plus square root of R by 2L whole square plus 1 divided by LC. You find that the right hand side of this equation is of the form a plus b into a minus b. So, by solving, we get omega 1 into omega 2 is equal to 1 divided by LC. But we know 1 divided by LC is equal to omega naught square. Therefore, omega naught square is equal to omega 1 into omega 2, or omega naught is equal to square root of omega 1 into omega 2, or f naught is equal to square root of f1 into f2. Hope you understood it. Friends, next we shall solve very simple problem on series resonance circuit. In this question, we are required to find f naught, q factor, bandwidth, f1 and f2 and I naught. All the data required to find the unknowns are given. We know that f naught is equal to 1 divided by 2 pi into 1 divided by root LC. By substituting L is equal to 0.01 Henry and C is equal to 0.01 microfarads and solving, we get f naught is equal to 15.91 kilohertz. Next, we know that Q is equal to omega naught L divided by R and omega naught is equal to 2 pi f naught. By substituting and solving, we get Q is equal to 99.96. Next, we know that bandwidth is equal to f naught by Q. By substituting and solving, we get bandwidth is equal to 159 Hz. Next, we know that f1 is equal to 1 divided by 2 pi into bracket minus r by 2l plus square root of r by 2l whole square plus 1 divided by LC. By substituting, r is equal to 10 ohm, L is equal to 0.01 Henry and C is equal to 0.01 into 10 to the power of minus 6 farads and solving, we get f1 is equal to 15.83 kilohertz. To find f2, we know that bandwidth is equal to f2 minus f1. Hence, f2 is equal to bandwidth plus f1. By substituting bandwidth equal to 159 into 10 to the power of minus 3 kilohertz and f1 is equal to 15.83 kilohertz, we get f2 is equal to 15.989 kilohertz. Finally, we know I naught is equal to V divided by R, and by substituting the values and solving, we get I naught is equal to 1 milliampere. Friends, next we shall solve third question on parallel resonance circuit to find the resonance frequency of the circuit shown in figure. Note that the voltage applied is not given. In fact, to find the resonance frequency in this circuit, the voltage is not required. Then strategy will be find the total admittance of the circuit and equate the imaginary part to 0. So, let Z1 is equal to R plus JXL and Y1 is equal to 1 divided by R plus JXL. By rationalizing it, we get y1 is equal to r divided by r square plus xl square minus j into bracket xl divided by r square plus xl square. Similarly, let z2 is equal to minus jxc or y2 is equal to 1 divided by minus jxc or y2 is equal to j times 1 divided by xc. By adding both y1 and y2 and separating the real and imaginary part, we get y is equal to r divided by r square plus xl square plus j into bracket 1 divided by xc minus xl divided by r square plus xl square. By equating the imaginary part to 0 and rearranging it, we get xl into xc is equal to r square plus xl square. But at resonance, omega is equal to omega naught and xl is equal to omega naught L and xc is equal to 1 divided by omega naught C. By substituting and solving, we get omega naught square is equal to 1 divided by LC minus R square by L square. Or omega naught is equal to square root of 1 divided by LC minus R square divided by L square. And f naught is equal to 1 divided by 2 pi into square root of 1 divided by LC minus R square divided by L square. It is so simple, isn't it? Friends, finally, we shall solve another problem on series resonance circuit. In this problem, we are required to find the circuit parameters R, L and C given the applied voltage equal to 230 volts at 50 Hertz, and it is also given that the maximum current is 15 amperes and quality factor Q is equal to 5. What does this mean? When the current is maximum, the circuit will be at resonance. So, I naught is equal to 15 amperes and F naught is equal to 50 Hertz. Now, we know that I naught is equal to V divided by R. Hence, R is equal to V divided by I naught and that is equal to 230 volts divided by 15 amperes and hence R is equal to 15.33 ohm. And Q is equal to omega naught L divided by R and that is equal to 2 pi F naught L divided by R. Hence, L is equal to Q into R divided by 2 pi F naught. By substituting the values and solving, we get L is equal to 0.244 henries. Also, we know that Q is equal to 1 divided by omega naught CR and that is equal to 1 divided by 2 pi F naught into CR. Hence, C is equal to 1 divided by Q into 2 pi F naught into R. By substituting the values and solving, we get C is equal to 41.5 microfarads. It is so simple, isn't it, friends? Friends, I hope that this tutorial has ignited some of your thoughts. If so, please forward your feedback and suggestions to my email. Thank you for watching this video.